Look at this tiny electronic component. It doesn't have a motor. It doesn't have a battery inside it. And yet, this tiny thing can store energy and release it extremely quickly. But here's the strange part. How can a small object like this store energy at all? When we hear the word store electricity, most of us imagine something like a battery. You put electricity in. You keep it there. And later, you take it out. So naturally, you might imagine that a capacitor is just a tiny battery. But it's not. So what is actually happening? Imagine I give you two flat pieces of metal. Like this. And then I place them very close together, but I make sure they never touch. Now here's the question, can these two pieces of metal somehow store energy? Take a second and think about it. If you were designing this device, where would you put the energy? Inside the top plate? Inside the bottom plate? Or somewhere between them? And most importantly, what could possibly exist between two pieces of metal that never touch? The answer is something you can't see with your eyes. An electric field. When charge builds up on these two plates, something changes in the space between them. The space isn't simply empty anymore. An electric field exists there. And this is the first big idea you need to remember. A capacitor stores energy in the electric field between its conductors. Think of it like stretching a rubber band. When the rubber band is relaxed, there's very little stored energy. But when you pull the two ends apart, you put energy into the system. The energy isn't sitting inside your hand. It's stored because of the stretched state of the rubber band. A capacitor has a surprisingly similar idea. Instead of stretching rubber, we separate electric charge. And that's why this tiny component appears everywhere. Phones. Computers. Cameras. Power supplies. Cars. Even the electronics controlling the device you're watching this video on. Because sometimes a circuit doesn't just need electricity. It needs energy to be available at exactly the right moment. And capacitors are incredibly good at helping with that. But we've just uncovered something strange. A capacitor can store energy without having its two parts physically connected. So now we have an even bigger question. If electricity isn't simply sitting inside the capacitor, what exactly are we storing? Is it electricity? Is it charge? Is it energy? And if energy is being stored, how much can we actually store? That's where the real story begins. Last time, we discovered something strange. A capacitor can store energy, even though its two metal plates never touch. And that leaves us with a very important question. If electricity isn't simply sitting inside the capacitor, then what exactly is being stored? Let's start with something we say all the time, the capacitor stores electricity. It sounds perfectly reasonable. But electricity isn't a substance like water that you can simply pour into a container. Electricity is what happens when electric charges move. And that tiny difference changes everything. So if electricity isn't the thing being stored, perhaps we're storing charge. And this idea is much closer. Electric charge is a property carried by particles. Electrons carry negative charge. Protons carry positive charge. And when we move these charges around, something interesting can happen. Imagine you have two boxes. One box contains 10 balls. The other contains 10 balls too. Nothing special, right? But now imagine moving all 10 balls from one box into the other. Suddenly, one side has too many, and the other side has too few. You've created a separation. And that separation can matter. But here's the important part. Moving those balls didn't happen for free. You had to do work to move them. And that work doesn't simply disappear. It becomes stored energy in the new arrangement. Think about lifting a ball from the ground onto a shelf. The ball is still the same ball. But now you've put it in a position where it has stored potential energy. You changed its position. And that required energy. A capacitor does something surprisingly similar. Instead of lifting a ball, we move electric charges apart. We put positive charge on one plate, and negative charge on the other. The charges are now separated. And just like lifting the ball required energy, separating those charges requires energy. That energy is now stored in the electrical arrangement between the plates. So we need to be careful with our words. A capacitor isn't really a little container filled with electricity. Instead, charge is separated, and energy is stored because of that separation. And this distinction is going to become extremely important later. But there's still something we haven't explained. We now have positive charge on one plate, negative charge on the other, and energy somehow stored between them. But why? What is happening in the empty space between those two plates? How can two objects that never touch each other still interact? The answer is something invisible. The electric field. In the last part, we discovered something important. A capacitor doesn't simply contain a little tank of electricity. Instead, energy is stored when positive and negative charges are separated. But that creates a much bigger mystery. How can those charges even affect each other when they're not touching? Think about two magnets. Put them near each other. You don't see a rope connecting them. You don't see a hand pushing them. And yet, they can pull toward each other or push away from each other. Something is influencing the space around them. Could electricity have something similar? Imagine placing a positive electric charge all by itself in empty space. Nothing is touching it. But if you bring another positive charge nearby, it gets pushed away. Bring a negative charge, and it gets pulled toward it. So the first charge has somehow changed the space around it. It has created an electric field. Here's an easy way to imagine it. You can't see wind. But you can see what wind does. Leaves move. A flag moves. Your hair moves. The effects reveal something invisible. An electric field is similar. You can't see the field itself. But you can see what it does to electric charges. Now come back to our capacitor. We have positive charges on one plate, and negative charges on the other. Each plate affects the space around it. And between the plates, their electric influence creates a strong, organized electric field. And now the strange part finally makes sense. Remember the energy we put into separating those charges? It didn't just disappear. The electric field is where that stored energy is associated with the arrangement of the charges. So the capacitor isn't a box filled with energy. It creates a particular electrical arrangement, and that arrangement creates an electric field. Think about a hill. A ball sitting at the bottom has very little gravitational potential energy. Move the ball up the hill, and you've put energy into the system. The ball now has a different position in a gravitational field. A capacitor is different, of course, but the intuition is similar. Energy can be associated with a field and the arrangement of objects inside it. But we've just created another mystery. Suppose I build one capacitor, and you build another. Both have two metal plates. Both can create an electric field. So why would one capacitor be able to store more charge than the other? What makes one capacitor better at storing charge? Is it the size of the plates? The distance between them? Or something else? That's the question that leads us to capacitance. We've now seen that separated charge creates an electric field, and that electric field is associated with stored energy. But here's something interesting. Not all capacitors are equally good at storing charge. Some are tiny. Some are huge. Some can store a little. Others can store thousands or even millions of times more. So what makes a capacitor better at storing charge? Let's forget electricity for a moment. Imagine two water tanks. One is the size of a bucket. The other is the size of a swimming pool. If you pour water into both, which one can hold more? Obviously, the swimming pool. We would say it has a greater capacity. And that's exactly the kind of question we're asking about a capacitor. But what determines the capacity of a capacitor? Remember the two metal plates from the previous episode? Let's make them bigger. Instead of a small pair of plates, imagine we spread them out. Now there's more surface available for charge to accumulate. In general, larger plates mean greater capacitance. It's a little like replacing a small bucket with a larger one. But there's another trick. What if we keep the plates the same size, and simply move them closer together? Something interesting happens. The electric interaction between the two plates becomes stronger. And the capacitor can store more charge for the same voltage. So, in general, smaller distance means greater capacitance. So now we have a simple pattern. Want more capacitance? Make the plates larger. Bring them closer. But wait, there's still a problem. What if we put some material between the plates? Could that change anything? After all, it's just sitting in the gap. How could that possibly affect how much energy the capacitor can store? Surprisingly, yes. Put the right insulating material between the plates, and the capacitor can store more charge for the same voltage. This material is called a dielectric. Different materials affect the electric field differently. And engineers use this to make capacitors with very different characteristics. So we've discovered something important. The ability of a capacitor to store charge for a given voltage depends on its physical design. Plate area, plate separation, and the material between them. We need one number to describe this ability. And that number is called capacitance. We can describe capacitance with a very simple relationship, C equals Q divided by V. In plain English, capacitance tells us how much charge a capacitor can hold for each volt across it. A larger capacitance means more charge can be stored at the same voltage. But knowing that a capacitor can store charge is one thing. How do we actually put that charge onto the plates? What happens when we connect a capacitor to a battery? Do the charges rush in instantly? Or does something else happen? That's where charging begins. In the last part, we learned that a capacitor's capacitance tells us how much charge it can store for a given voltage. But there's one problem. How do we actually get the charge onto the plates? Imagine we have a battery, and an empty capacitor. We connect them with wires. What happens next? Maybe the capacitor fills with charge, just like filling a water tank. So perhaps the moment we connect the battery, the capacitor should become completely charged. Instantly. Right? Let's find out. We close the switch. The battery creates a voltage difference across the circuit. That pushes electrons through the wire. Electrons leave one capacitor plate, travel through the circuit, and accumulate on the other plate. And now something important begins to happen. One plate becomes more positive. The other becomes more negative. Remember what we learned earlier? Separated charge creates an electric field. So as more charge builds up, the electric field between the plates becomes stronger. But there's something else happening. As the capacitor becomes more charged, the electric field between the plates becomes stronger. And that field begins to oppose the further separation of charge. In other words, the more we charge the capacitor, the harder it becomes to add more charge. And this gives us a useful way to think about the whole process. The battery is continuously providing the push that moves charge. The capacitor is building up an electrical separation. The battery supplies energy, and the capacitor stores that energy in the electrical field. Eventually, the capacitor reaches a point where its voltage matches the battery's voltage. At that point, there is no longer a reason for charge to keep accumulating. The capacitor has reached its charged state. The battery may still be connected, but the capacitor is no longer continuously filling with more charge. But wait. We just said something that sounds simple: connect the battery, and the capacitor charges. But think about it. If electrons can move through a wire extremely quickly, why doesn't the capacitor charge instantly? Why does charging happen gradually? What controls how fast it charges? And what happens if we put a resistor in the circuit? That's where things get really interesting. In the last part, we connected a battery to a capacitor. Charge started moving, the electric field grew, and eventually, the capacitor reached the battery's voltage. But there's something we haven't answered. Why didn't it happen instantly? After all, electrons can move through wires extremely quickly. Imagine you're filling a large water tank. You have plenty of water available. But there's a problem. The water has to travel through a very narrow pipe. So even though the water source is huge, the tank doesn't fill instantly. The pipe controls how quickly water can enter. In an electrical circuit, we have something with a similar job. Resistance. Resistance makes it harder for electric current to flow. More resistance means less current can flow at a given voltage. So if the battery is the source pushing charge, the resistance controls how quickly that charge can move. But here's where the capacitor makes things interesting. When the capacitor is completely empty, there's almost no voltage across it. So at the beginning, the battery has a strong push to move charge. Charging starts quickly. But as charge builds up, the capacitor's voltage rises. And that voltage pushes back against the battery's attempt to add more charge. So something beautiful is happening. At the beginning, big difference, strong current, fast charging. Later, smaller difference, weaker current, slower charging. And finally, no difference, no net charging. That's why a capacitor doesn't charge at one constant speed. It charges fast at first, and then gradually slows down. Now let's change the resistor. Keep the same battery. Keep the same capacitor. But use a larger resistance. What happens? The charging process becomes slower. Use a smaller resistance, and the capacitor charges faster. But resistance isn't the only thing that matters. Remember capacitance? A capacitor with a larger capacitance can hold more charge for the same voltage. So, with the same resistor, a larger capacitor also takes longer to charge. Engineers wanted a simple way to describe this charging speed. So they combine these two properties, resistance and capacitance. Multiply them together, and you get something called the time constant. It's written as tau equals R times C. You don't need to memorize it yet. Just remember the idea. RC tells us the timescale of the capacitor's response. And now we know how a capacitor charges. Slowly. Predictably. But we've only looked at one direction, putting energy into the capacitor. What happens when we suddenly give that stored energy somewhere to go? How quickly can it come back out? That's where the capacitor becomes really powerful. Remember the mystery we started with? A tiny electronic component, somehow producing a powerful burst of energy. Now we finally have enough pieces to understand what's happening. The capacitor is charged. Energy is stored in its electric field. But here's the interesting question: what happens when we suddenly give that energy somewhere to go? Imagine a dam holding back a huge amount of water. The water has nowhere to go. So the energy is simply waiting. Now imagine opening a gate. Suddenly, all that water has a path to move through. The important thing isn't just how much water exists. It's also how quickly you let it move. A charged capacitor is surprisingly similar. While it's disconnected, the energy remains stored in its electric field. But connect the two plates through a circuit, and you've created a path for charge to move. The stored energy begins to leave the capacitor. The capacitor is discharging. And now the energy can do useful work. It can move current through a light. It can create a pulse. It can power a circuit for a brief moment. The capacitor doesn't need to hold the energy forever. Its real strength is that it can release stored energy when the circuit suddenly needs it. But why can this happen so quickly? Because the energy was already stored. We aren't waiting for the battery to slowly generate it. We're releasing energy that was stored earlier. It's like a stretched spring. You slowly stretch it, but when you let go, the stored energy can be released very quickly. And remember what we learned in the last part? Resistance controls how quickly charge can move. So if we give the capacitor a low resistance path, energy can come out very quickly. Give it a high resistance path, and the release becomes slower. The same capacitor can therefore behave very differently, simply because of the circuit connected to it. And now we can finally return to that tiny camera flash. The capacitor is charged slowly by the circuit. It stores energy. Then, when the camera needs a burst of light, a switch rapidly creates a path for that stored energy. The capacitor discharges through the flash circuit. And for a very short moment, a large amount of power is delivered. So the capacitor didn't magically create energy. And it didn't behave like a tiny battery. It did something more subtle. It stored energy ahead of time, and released that energy when the circuit needed a sudden burst. But now comes a question we've completely avoided. We've been saying, the capacitor stores energy. Fine. But how much? Is it a tiny amount? Does doubling the voltage double the energy? Or does something much more interesting happen? Let's put a number on that energy. We've spent the last 7 parts discovering that a capacitor can store energy. We know where that energy comes from. We know how it gets stored. And we know how it can be released. But we've avoided one very important question. Exactly how much energy is actually stored inside a capacitor? Obviously, not every capacitor stores the same amount of energy. A tiny capacitor can't store as much as a large one. And a capacitor charged to a higher voltage can store much more energy than the same capacitor charged to a lower voltage. So there must be some relationship between capacitance, voltage, and energy. Remember something we learned earlier? Capacitance tells us how much charge a capacitor can store for a given voltage. We wrote it as C equals Q divided by V, rearranging that gives us Q equals C times V. So if we increase the voltage, the capacitor holds more charge. But does more charge automatically mean more energy? Think about filling a water tank. At the beginning, pushing water in is relatively easy. But as the water level rises, the pressure at the bottom increases. So the later water you're adding is being pushed against a greater pressure. You're doing more work to put it there. A capacitor behaves in a surprisingly similar way. When we charge a capacitor, we're doing something similar. At the beginning, there's little voltage across the capacitor. So adding a small amount of charge requires relatively little energy. But as the capacitor charges, its voltage rises. Adding the next bit of charge requires more energy than adding the first bit. So the energy isn't simply charge multiplied by the final voltage. The voltage changes throughout the charging process. If the voltage started at 0, and gradually increased to the final voltage, then the average voltage during charging is half of the final voltage. So the stored energy becomes energy equals charge multiplied by average voltage. which gives us E equals 1/2 QV. And we already know Q equals CV. So replace Q with CV. And something beautiful happens. We get E equals 1/2 CV squared. Look carefully at that equation. Voltage is squared. That means if you double the voltage, the stored energy doesn't simply double. It becomes 4 times larger. That's a huge difference. And it's one reason voltage matters so much when designing capacitor systems. And now something else should seem strange. If capacitors can store energy, and release it when needed, why are there so many tiny capacitors scattered across almost every circuit board? A phone can have hundreds of them. A computer can have thousands. What are all those tiny capacitors actually doing? That's where capacitors stop being just energy storage devices, and become the quiet heroes of electronics. We've just learned that a capacitor can store energy. So you might expect capacitors to appear only where we need a lot of stored energy. But look at almost any circuit board. You'll find tiny capacitors everywhere. Near processors. Near memory chips. Near sensors. Near power connections. Why? These tiny capacitors often store very little energy. So why are they everywhere? Imagine a processor suddenly starts doing a lot of work. For a tiny fraction of a second, it may need more current than it was using a moment ago. Then it needs less. Then more again. And this can happen millions or even billions of times as electronic circuits switch. So the power being demanded by a chip isn't perfectly smooth. It constantly changes. But the chip isn't sitting directly inside the power supply. Power has to travel through wires and circuit traces to reach it. And those connections aren't perfect. They have resistance. They also have tiny amounts of inductance. So when the chip suddenly asks for a burst of current, the power supply can't respond perfectly instantly. Think about a house connected to a huge water tank far away. Normally, the pipe supplies the water you need. But suddenly, everyone in the house opens a tap at the same time. The distant tank can't instantly send extra water through the entire pipe. So what if we placed a small water tank right next to the house? During those sudden moments, the nearby tank could immediately help. A capacitor placed close to a chip acts like a tiny local reservoir of electrical energy. The power supply provides the average energy. But when the chip suddenly needs a short burst, the nearby capacitor can provide some of that current locally. And when the demand falls again, the power supply can recharge the capacitor. Without that nearby reservoir, sudden changes in current could cause the voltage at the chip to fluctuate. And electronic circuits don't like unstable power. Too much fluctuation can cause incorrect operation, noise, or even malfunction. So that tiny capacitor is helping keep the local supply voltage stable. And there's a small detail that makes a huge difference. The capacitor needs to be close to the circuit it's helping. Why? Because if we put our little energy reservoir far away, the current still has to travel through the same unwanted resistance and inductance. The whole point is to provide the current right where it's needed. And suddenly, the thousands of tiny capacitors on a circuit board make sense. They aren't all there because the circuit needs enormous amounts of stored energy. Many are there because electronics constantly experience tiny, extremely fast changes. The capacitor helps absorb those changes locally. It's a small component solving a very fast problem. But here's the thought experiment. Imagine we remove every capacitor from your phone. No tiny capacitors near the processor. No capacitors near the memory. No capacitors helping the power supply. Would the phone still work? Or would something much more fundamental break? Let's find out what electronics would look like without capacitors. In the last part, we discovered why tiny capacitors are scattered across electronic circuits. They help provide short bursts of current. They help keep power stable. They help deal with rapid electrical changes. But let's try something strange. What if we removed every capacitor from electronics? Not one. Not 10. Every single one. Let's start with something we've already seen. A processor doesn't always consume the same amount of current. Its demand constantly changes. With capacitors nearby, those sudden changes can be softened. Remove them, and the power supply has to deal with those changes much more directly. Think back to our water system. Imagine a city with pipes, but no water tanks anywhere. Every time thousands of people suddenly open their taps, the entire supply system has to react immediately. Reservoirs make the system much more stable. Capacitors play a similar role in many electronic circuits. They provide a little local reserve exactly where it's needed. But power instability isn't the only problem. Electronic circuits also deal with unwanted electrical fluctuations. Tiny rapid variations can ride on top of the signal or power supply. And sometimes, we don't want those variations at all. Capacitors can help smooth them out. And this brings us to something fascinating. A capacitor doesn't simply respond to voltage. It responds differently depending on how quickly that voltage changes. Slow change. One kind of behavior. Rapid change. A very different behavior. And that single property makes capacitors incredibly useful for filtering signals. And this is where the capacitor becomes much more interesting than our original idea of a simple energy tank. Depending on how we connect it, a capacitor can store energy, provide short bursts of current, smooth a power supply, filter unwanted signals, help create timing delays, and even help signals move from one part of a circuit to another. So removing capacitors wouldn't simply make one particular component disappear. It would remove an entire collection of tricks engineers use to control electricity. Some simple circuits would still work. But many practical electronic systems would become harder to stabilize, harder to filter, harder to time, and harder to make reliable. And that's the strange thing about the capacitor. It isn't powerful because it does just one job. It's powerful because its fundamental behavior can be used in many different ways. Store something. Release something. Smooth something. Block something. Pass something. All using the same basic component. But now we've arrived at one of the strangest things about a capacitor. Remember what we just said? It behaves differently when voltage changes slowly versus quickly. But why? What exactly does the capacitor care about? And can we describe that behavior with a single equation? Yes. And that equation will reveal something we haven't seen before. A capacitor responds not simply to voltage, but to how fast voltage changes. We've reached a strange point. We know a capacitor stores energy. We know it can release that energy. We know it can smooth sudden changes. And we've even seen that it behaves differently when voltage changes slowly versus quickly. But why? What exactly does a capacitor care about? The voltage itself? Or something else? Let's forget everything complicated for a moment. Remember the most basic relationship we've already learned. A capacitor's charge depends on its capacitance and its voltage. Q equals C times V. So here's the important observation: if the voltage changes, the charge on the capacitor must change too. And what does it mean when charge changes? It means charge has to move. And the movement of electric charge is what we call current. So we've just uncovered something important. When the voltage across a capacitor changes, its stored charge changes, and that requires current to flow. But here's where things get really interesting. What if the voltage changes slowly? Only a little charge needs to move each moment. So the current is relatively small. But what if we change the voltage very quickly? Now the capacitor has to change its stored charge much faster. Which means more current must flow. Think about our water tank again. If the water level rises very slowly, only a small amount of water needs to enter each second. But if you want the water level to rise extremely quickly, you need a huge amount of water flowing in every second. Same tank. Same water level. The difference is simply how quickly the level is changing. We can describe current as the rate at which charge changes. In other words, current equals the change in charge divided by the change in time. Mathematically, I equals dq dt. But we've already learned another relationship, Q equals C times V. So if charge depends on voltage, then the rate at which charge changes depends on the rate at which voltage changes. Substitute Q equals CV into our current equation. And we get I equals C times dV dt. And suddenly the strange behavior of the capacitor makes sense. If the voltage isn't changing, then the rate of change is zero. So ideally, capacitor current becomes zero. But if voltage changes quickly, the rate of change becomes large. And the capacitor current becomes large too. The faster the voltage changes, the harder the capacitor responds. So maybe the capacitor's true superpower was never simply storing energy. It's responding to change. That's why the same tiny component can stabilize power, filter signals, create timing behavior, and store energy. And now, after everything we've discovered, we can finally ask the simplest question of all. What is a capacitor, really? Is it a tiny battery? Is it an energy tank? Is it a filter? Is it a timing device? Or are all of these just different ways of seeing the same thing? Let's put the entire journey together. 12 parts ago, we started with something incredibly ordinary. Two pieces of metal. Separated by an insulator. Nothing moving between them. And yet, this tiny object can store energy, release it in a burst, stabilize a processor, filter electrical signals, and help control timing. How can one simple component do all of that? Let's rebuild the whole idea from the beginning. Apply a voltage across a capacitor, and charge begins to separate. One plate becomes more positive. The other becomes more negative. The separation of charge creates an electric field between them. The energy isn't stored as little balls of electricity sitting inside the capacitor. It's stored in the electric field created by that separated charge. How much charge can we separate for a given voltage? That's where capacitance comes in. We learned Q equals CV, capacitance tells us how much charge corresponds to a given voltage. Bigger capacitance means more charge for the same voltage. But separating charge requires work. And that work becomes stored energy. We eventually discovered E equals 1/2 CV squared. And remember the surprising part. Voltage is squared. So double the voltage, and you get 4 times the stored energy. And that stored energy doesn't have to stay there. Give the charge a path to move, and the capacitor discharges. The stored energy can flow into the surrounding circuit. That's how a capacitor can produce a brief burst of power. Store first. Release later. But here's where the capacitor becomes much more interesting. It doesn't only care about how much voltage exists. It also cares about how quickly that voltage changes. Because voltage changes, charge changes, and changing charge means current. Which gives us I equals C times dV dt. And suddenly, all those different applications start making sense. Need a temporary energy reserve? Capacitor. Need to smooth a power supply? Capacitor. Need to reduce certain unwanted fluctuations? Capacitor. Need timing behavior. Capacitor. Need to couple or separate changing signals in a circuit. Capacitor. So is a capacitor a battery? Not really. Is it just an energy tank? Not really. Is it a filter? Not by itself. Is it a timing device? Not by itself. These are different ways we use the same physical behavior. At its heart, a capacitor is simply a device that stores energy in an electric field created by separated charge. And because its stored charge changes when its voltage changes, that simple behavior lets us control energy, current, signals, and time. That's the capacitor. Two conductors. One electric field. And an enormous number of possibilities.